for today's lesson, we'll be learning about systems of differential equations. In particular, we'll be looking at real eigenvalues. Systems of differential equations are multifunction differential equations. Eigenvectors are vectors x in the same direction as x, and eigenvalues are the values of the vectors change in length. So eigenvectors and eigenvalues come from this definition, ax is equal to lambda x. The symbol here is lambda. For example, we have dx over dt is equal to 3x, and dy over dt is equal to x plus m and 1. Here we have two differential equations form a system. Because there's more than one differential equation, this is a system. So now we can rewrite this in a system form, in a matrix form. So here we use capital Y. We could use any variable besides x and y just to denote that this is the system. So I've called the system capital Y. So dy over dt is equal to 3017y. This 0 comes from here. There's actually a 0y here. We need, when doing matrices, you include all the x terms, the y terms, and so forth. So with this right here is the coefficient matrix A. A is equal to 3107. Now, in order to find the eigenvalues necessary to solve the system, we have to take the determinant of A minus lambda I. So basically, we subtract lambda across the diagonals of the coefficient matrix. And then we set it equal to 0 to find our eigenvalues. So 3 minus lambda, 0, 1, 7 minus lambda. The determinant of this is equal to 0. Now, in order to find the determinant of a 2 by 2 matrix, this is 2 by 2 because there are 2 rows and 2 columns, we multiply this diagonal and subtract it by the product of this diagonal. So 3 times lambda times 7 minus lambda minus 0 times 1 is equal to 0. This gives us eigenvalues of lambda equal to 7, lambda equal to 3. If you were to distribute all these terms, you would actually form what is known as a characteristic equation. Lambda squared minus 10 lambda plus 21 is equal to 0. Now, with these eigenvalues are corresponding eigenvectors. So now we will work with the first eigenvalue, lambda equal to 7. For lambda equal to 7, what we're going to do is subtract the value 7 across the diagonal in a matrix form. However, instead, right here, we're going to have 0 and 0. This line is here because these two equations are both equal to 0. So now with this, we have negative 4, 1, 0, 0, and 0, 0. We find that we can get an all 0 row if we just add 4 from this row to this row. So this cancels the negative 4. We have this all 0 row and 1. However, we want to swap these because this value right here is for x1. So now we have x1 is equal to 0. However, we have this all 0 row. So this implies that the next variable y1 is free. Since it is free, we can assign it a value. So we're going to just let y1 equal to 1. And then we get the eigenvector 0, 1. So we also get a straight line solution from our y value. y1 is equal to 1. This will all make sense as we construct our phase portrait. And then we have lambda equal to 3, our other eigenvalue. And we have, so now subtracting 3, 3 minus 3, 0, 0, 1, 7 minus 3, and 0. We find that this 2 also has an all 0 row. So now we swap these two. So now we have this all 0 row, very similar to this one. However, we have a 1 and 4. So this implies that x2 plus 4y is equal to 0, and y2 is equal to y2 again. Since y2 is free, we could let y2 is equal to 1. So this implies that x2 is equal to negative 4y2, and y2 is equal to negative x2 over 4. So we get another straight line solution, y2 is equal to negative x2 over 4. So our corresponding eigenvectors are the coefficients in front of x2 and y2 for this particular one. So our eigenvectors, negative 4 and 1. This eigenvector corresponds to lambda equal to 3. And then our general solution is just the combination of these two. The eigenvectors, the values. So for the general solution, we have y of t is equal to c1 e to the 7t times the eigenvector 0, 1 plus c2 e to the 3t times the eigenvector negative 4, 1. So these eigenvectors directly correspond to these eigenvalues. And these C1 and C2, they will change based upon initial conditions. In the problem, there were initial conditions y0 is equal to 1, 1. Now this may seem strange, but this right here just denotes t, or some other independent variable. That is the value we substitute for, and this will be for the first row, and this will be for the second row. So here, using the initial conditions, we have the first row right here, 1. Second row, 1, is equal to c1 e to the 0. So 0 was substituted for that t value, times 0, 1, plus c2 e to the 0 times negative 4, 1. So now we get 0c1 from here, minus 4c2 is equal to 1. c1 plus c2 is equal to 1. Here, because this is a 0c1, we get a c2 equal to negative 1/4, and now we can substitute the value in. So we have c1 is equal to 1 minus c2, which is equal to 1 minus negative 1/4, which is equal to 5/4. So now using these c1 and c2 values, we substitute them in to get our solution to our IVP. IVP just means initial value problem. So our solution is y of t is equal to 5/4 e to the 7t times 0, 1, minus 1/4 e to the 3t times negative 4, 1. Now, phase portrait just shows overall system behavior using eigenvalues, eigenvectors, and straight line solutions. So rather than having to draw slope fields, which would be very time consuming, very difficult, we can just use the eigenvalues and vectors to come up with overall ideas for system behavior. So the first thing to do when constructing a phase portrait is to get the straight line solutions. So we have one straight line solution, y1 equal 1. So that's just a horizontal line. y1 is equal to 1. We have our other straight line solution, y2 is equal to negative x2 over 4. That has a negative slope, so you just draw it down like this. Positive eigenvalues point away from the origin, and negative eigenvalues point towards the origin. So these arrows are pointing out. So on this line, they're pointing out, and on this line, they're also pointing out. Now that we have our two straight line solutions, now we can form the rest of the system. Because these two lines are coming out, we can draw this curve right here because it will never touch these values. And then we can do the same thing for each of these. This is straight, this is straight. We know it won't touch, but it will curve along these lines. So these are solution curves, but they do not touch the straight line solutions. So these also point out, and they go around like this. And these also point out because they're bounded by these lines. And these also point out, and they go in this direction because they're also bounded by these lines. Phase portraits are also used to show paths of motion. For example, maybe this is a particle, and depending at certain points on this coordinate system, it will turn in a certain given direction. So again, this is our phase portrait. And I hope this helped you in understanding differential equations, and thank you very much for watching.